and then restart the recording so that I have separate videos. Whoops. So I have separate videos for the YouTube, so it's not too long. So that was the lecture portion. I'm going to actually save this and start a new thing. I'll post that picture that I was working with online for you to look at if you want to. And we're going to start some example problems now. Neil's question. For the first homework problem, I got a negative number of electrons for one of the fruits. Is this possible or wrong? Not possible to have a negative number of electrons. You can have 0, but you can't take electrons away from 0. And also, I'll get to your question in a minute, Jacob. So yes, it's wrong to have a negative number of electrons. I don't want to say too much because it gives away the trick of that problem. I'll say this. How about this? What if you have like, it's an apple and an orange, right? What if you have like a mini orange like this big, and then you have a big old apple boy like 4 times its size? Or vice versa. Think about that. Jacob's question. In the table I showed had ohm meters or ohm centimeters. Do we need to know which one to use? It'll be ohm meters when we get to resistivity, but for now, don't worry about that. That's the unit for resistivity, not resistance. Resistance itself is just ohms. In fact, I don't know why they were using ohm centimeters. That's a really bizarre unit, but it'll always be ohm meters by default. Just always ohm meters. Other questions? Do you want to work that second problem on the homework? I want to leave the first problem for you to puzzle out because I think it's a nice thought experiment. But we can work on the second problem if I can remember where I put it. There it is. You wanted to try the second problem? Great. I'm happy to let you guys try it. How about this? Instead of that, let me pull up the original homework before I reduced it by half, and we'll work on one of the other problems that I didn't assign you this week. This one we can't do yet because it's circuits. Oh, right. I forgot. That was the only one. Yeah. Because this one is this question 4 here. A typical wire in a circuit is composed of a core of copper surrounded by a casing of plastic. Why are wires designed this way? What role does each layer play in a circuit? Well, there's a very quick answer to that, which is copper, as we saw in those tables, is a really good conductor, so it lets electrons flow easily, and plastic is a really bad conductor, or a very good resistor, so it doesn't let electrons leak out of the circuit. That's essentially the entire part of it, that you want electrons to flow along the circuit, but not out of it. And if you're flowing out of it, that's probably going to electrocute you, or other things around it. So that bad, as we say in science. Let me see if I can invent a question for you. Okay. Let's have a circuit. This is like the absolute simplest possible circuit to draw. What it is just 2 terminals, which just means like 2 ends of the wire, basically. And then in the middle of them this is a resistor. So next week we're going to talk a lot about circuit elements, but there's a few standard ones. You know, here's a voltage source, and this is a resistor. There's a capacitor. There's an inductor. All sorts of things go in a circuit. You don't need to know any of these symbols right now. Just know This one, the little scribble guy, is a resistor. In real life, a resistor, most, not all of them certainly, and certainly an integrated circuit board, they don't look like this, but you can buy, I'm sure I have a whole ton of them here somewhere. Oh, I know where, I actually know exactly where I have some. In real life, they look like little peanuts, like little tiny peanuts. There's a wire going into them, and they have these stripes, color-coded stripes on them, like that. In fact, if you'll excuse me for just a minute, I'm going to go fetch a resistor or a couple of resistors to show you. I'll be right back. Okay, here we go. Here's a whole bunch of resistors. These are 27 ohm resistors. I don't know if you guys can see these very well on the webcam, because I didn't focus at all. You see little peanut guys? And they got the colored stripes on them. Anyone? Yeah. So the colored stripes are actually like a little code that tells you what the resistance of each resistor is and the error on that. So there's manufacturing errors based on the manufacturing process. So it might be a little bit more, a little bit less than 27 ohms. I don't actually remember how accurate these ones are. It's a gold ring, so I think it's, yeah, the blue thingies are the resistors. Little peanut looking boys. I think a gold ring is plus or minus 1%. We can look up a table of that later. I always have to look it up. I can never remember the color coding for resistors. This one is it's like red, brown, black, gold, brown. I think the extra, well, we'll talk about all that next week. I think, don't want to get into the weeds with it too much. But yeah, those are real resistors. I have a whole ton of them out in my shop for electrical work. All sorts of different values. This is a strip of 27 ohm ones. Anyway, so this circuit that I've drawn here is essentially like just one of these resistors. Nothing else to it. Just like one of these boys in the middle, and then the two sides of the wire on either side. That's all I've drawn there. So let's imagine that, yeah, this resistor has a value of 27 ohms, just like the real ones I have in front of me here. And I apply, let's say I apply a voltage across it. Someone give me a nice number. Type in any number into the chat. 8. 8 volts being applied across it. So if we use Ohm's law, V equals IR, we can figure out the current going through it, the electrons per time, or the charge per time. So V equals IR, we want to figure out current, so I equals V over R, so 8 over 27. I need a calculator for that, because that's not a nice thingy. .29626. 0.296 repeating amps. So that's the current going through that resistor. So I have, let's see, could we get 8 volts? Standard AA battery, which I have a ton of, are 1.5. So we get 9 volts across it. So I mean, a AAA battery is also 1.5. 9-volt battery is obviously also 9 volts. We could undervolt. We could like discharge a typical battery a little bit, and we could probably get 8 volts across it. So I could probably work out something that actually runs 8 volts across this to get 0.296 amps running through a resistor. You need a battery holder, and you'd need 6 AA batteries probably to do that. But totally doable. One thing to mention, at full charge, when you have fully stored up with electrons in a battery, AA's and AAA's, and even I think like D batteries and C batteries, like the big ones, those are around 1.5, 1.6 volts. They're supposed to be 1.5, but they might overvolt a little bit if they're full up. And as you discharge them, as you get less electrons, or really, it's not really less electrons, it's more like less organized electrons, the voltage drops. I have, for my little miniature drone, I have batteries that I can't remember how, I think they're 7.4 volts. So that's pretty close to 8. In fact, if you overvolted a little bit, it'd probably be around 8. Yeah, and as it discharges, the voltage drops. So you can think of it as like you have a lot of electrons stored up in there, and as it discharges, they kind of slowly leak out. It's not exactly what's going on, but as it discharges, the ability for it to provide that pressure for the electrons to flow through a circuit, like the pipe, drops. So yeah. Okay, how about a second part of this sample problem, and then that'll be it. How you guys feeling? Thumbs up, thumbs down, thumbs sideways? Okay. Let's do a second part of this sample problem where we figure out the number of electrons flowing past this, or through the resistor, with this current going on. So we know the amount of current. Oh, hey, trivia question, meaningless trivia question. What is this bar called? I know I've told you guys this before. Anyone? I'm gonna write it down. Vinculum. Repeat Magi. Okay, so yeah, it's called a vinculum. One of my favorite math words. Okay, so if this is the current, recall that we defined the current as the amount of charge flowing across a point or through a point divided by the amount of time it took to flow. So let's say, we want to find out, like in 1 second, which is going to make the math easier, how many electrons flowed through this resistor in 1 second of this voltage. So there's your current. Delta T is going to be equal to 1, so that makes the math way easier. So delta Q is going to be 0.296 vinculum amps times 1 second is going to be equal to 0.296. Anyone remember the unit here? Amps times seconds. Amp seconds is coulombs. Hooray for charge. And then to get the amount of electrons, the number of electrons, we're going to divide this by the elementary charge. Yay! Which, anyone who remembers it, type it into chat. guess you could look it up too. Yay, branch. Okay. 1.602 times 10 to the negative 19, not negative 9, coulombs. So it's going to be 0.296 repeating over that bad boy. So the number of electrons is going to be, I have to plug this into a real scientific calculator. Give me a second. Divided by... I can't type today, you guys. I get 1.85 times 10 to the 18. Anyone else agree with that? Hey! Great. So 1.85 times 10 to the 18, 10 to the 18 is a lot. What is it? 10 to the 9 is a billion. 12 is a trillion. 15 is a quadrillion. So 10 to the 18 is quintillion. 1.85 quintillion electrons flowing through that that resistor in one second. That's crazy. And that is actually, that's probably a very realistic, like, that's absolutely doable. I could easily, not that easily because I don't have the right voltage, I could easily rig up a 9-volt battery across one of these resistors, and I'd have, you know, even more electrons flowing across it in 1 second. Which is kind of the remarkable things about electrons being so teeny tiny. There's a lot of them. A lot of them. Okay. How you guys feeling? Feel like we're good here? I don't need to keep you longer than I should. In fact, actually, hold on. What time did we start? We started at 10:30? Okay. We have about 15 minutes. 15 minutes left. Good. Do you guys need more? Do you feel like you can approach the homework now? Because I think this here is very similar to what we're doing on the homework. Although it's not exactly the same. So you can attempt it yourself. I put up an assignment on Classroom so you have a place to upload files to, if that helps. You can still just email them to me. Either way is going to work, as long as it gets to me. I wanted it just by the end of day Thursday, midnight Thursday, or whatever, 12:01 Friday, whatever. Just because Friday is supposed to be a holiday. Not that that has much meaning anymore these days, it feels like. But I did want to give you guys some time to not have to do work, because I've been hearing a lot that classes are giving a lot of work, and it just feels like a lot right now, which I totally get. But does this feel manageable? They can be either. You can type them up or you can handwrite them. Does not matter to me. Excellent. This sounds good, you guys. Next week is going to be more work because we're going to start looking at circuits. I'm trying to find a good interactive online where you can actually play with a simulation of a real circuit. If we were in class this week, you would be actually building little circuits with the little circuit snap kits I've got. Unfortunately, we can't do that. So I'm going to try to find, and I know I will find, because there's a ton of things out there, something that you can play with. There's going to be another homework next week, maybe a little bit longer, but not much longer than this current one. And we're going to go over resistivity, how to calculate the resistance of any given object. We're going to go over actual circuit elements, like what they are, all these guys that I mentioned up here. Can we go through the homework on Thursday? Absolutely, we can go through the homework on Thursday. We're scheduled for 8 a.m., I want to say. Is that right? 8:20? Ugh. Not required, guys. I'll be here, but not required. Um, yeah, I think that's that. Ugh, first block. Blech. Next week, I'm gonna make the only reason I scheduled us for first block because it was the only other time. Yeah, Isabel, you don't have to be there. Um, don't feel bad if you're not there. I'll barely be there. Like it was hard enough for me to get up for 10:30. um, what was I gonna say? The only reason I scheduled a first block is because we only had 2 meetings scheduled this week. There's nothing on Friday, and I wanted to give you guys a chance for this lecture, but also for the actual homework to have questions once you've actually looked at it for a couple days. Next week, when we have 3 classes scheduled: Monday, Wednesday, Friday. Next week, is that right? No, because we have Friday off technically this week. We're again scheduled for Tuesday, Thursday. Let's hope that one of them is not first. I don't think it is. I can actually check that really quick. I don't think we're scheduled for that, but I'll try to have it scheduled for both. Both times. Physics 2. So we are 10:30, 11:40 on Tuesday next week, and we are 12:25 to 1:50. So we'll have both again next week. Do you think do you feel like this session with me doing like live lecture and then questions was good, or would you rather have? This was my experiment. Would you rather have like a video where I just go through this lecture and then we have a question session later? Because I've been doing that with Physics 1, and I haven't yet had a question session with them to ask how it's going. I'll have them next. Would you prefer one or the other? I can tell you this way is a lot less work for me, but it's less polished as well. So, no. Yeah, okay. I might just stick to this streaming format then, because it's a lot less work for me. Let me tell you, video editing is so hard for no reason. Yeah, okay. And what I'll do is I'll take the recordings of this session. There's 2 parts of it. There's this problem session, and then there's the lecture, and I will post them on my YouTube channel. I'll post them on the links on Classroom, so you can come back and watch this anytime. I will save these pages, and I'll figure out somehow to actually also post these on Classroom, these notes as well on Classroom. Sound good? All right, if there's not anything else, then we will adjourn class. It's Jub Jub. Who are you? I need to know, are you one of my missing peoples? Nito Burrito. Julian? Well, it's good to see you, Julian. I'm glad you were able to come by class. Any quotes for the Twister? Oh, nothing yet. Keep on the lookout for that, though. Okay, then I guess class dismissed. I will see you guys. If you want to be here, not at all required. I'll see you guys for another Q&A session right here. Josh, you're here. My goodness, Josh. 12 out of 14. That's not bad, you guys. That's not bad. So yeah, I guess I will see you guys back here Thursday if you want to be here at 8:20 a.m. I will have tea, like a lot of black tea with caffeine in it. And yeah, that's that. Thanks so much for coming. Have a wonderful day. If you have any other questions that you like think of in the middle of the night, send it to me. You don't have to obey time guidelines. Send it to me anytime. I might not always get back to you immediately, but I will do my best. And take care, guys. Take care. It's good to actually talk with you. It's good to see your color-coded screen names, at least in the chat. All right. Bye.